Okay, our next lesson is on solving rational inequalities. So of course an inequality is different than an equation because instead of an equal sign you have like a greater than or a less than or a greater less than or equal to or whatever else. So in this course we have already looked at polynomial inequalities, such as this one right here, which is just a linear inequality. Let's just go through how we solve that. So when we have a linear inequality, we usually just start off by treating it like it's an equation. Okay, and I can subtract 12 from both sides and get negative 2x is greater than 8. And then you might be tempted to say, okay, divide both sides by negative 2, and my answer is x greater than negative 4. That's incorrect, though. And if you look at the line above right here, you should see why. So if x is greater than negative 4, then an answer might be 5. 5 is greater than negative 4. Well, negative 2 times 5 is negative 10, and negative 10 is not greater than 8. Okay, another answer that's greater than negative 4 might be negative 3. Remember that negative 3 is greater than negative 4. The greater than sign refers to where numbers appear on the number line. So for example, negative 10 million is a very small number in that respect. So negative 3 might be an answer, but negative 2 times negative 3 is 6, and 6 is not greater than 8. So we actually have the exact opposite of all the answers we want. The real answer is x is less than negative 4. So a simple rule here is when you're solving an inequality like this, if you divide by a negative number, then you flip the inequality. So greater than becomes a less than, and vice versa. Now, just like with equations, we can represent this graphically. I'll pull up Desmos and let's just take a look at that. So the left side of the equation was 12 minus 2x. So I'm going to graph y equals 12 minus 2x. Okay, and I get a line. And the right side was just 20. So what I'll do here is I'll just graph y equals 20. Okay, now we were looking for when is 12 minus 2x greater than 20? And if we look at where these graphs intersect, sure enough, that's at the point negative 4. We can see that the blue line is higher than the green line when x is less than negative 4. And so the solution is visible on the graph here, anything less than negative 4. Okay, moving on to another example. This is a nonlinear, obviously, inequality. This is a polynomial inequality. We've done these already as well. No matter how you do this, the first thing is to factor. Now, the factoring is quite a bit of work. I'm not going to cover that here. There's definitely a common factor of x. And then you can use the factor theorem and long division to divide the remaining cubic. And this is what you get right here. So how do we solve this? Well, there were a couple options. One option was what we called the graphical solution. So we actually can graph this equation and just see when it's greater than or equal to 0. Okay, so it's a degree 4 polynomial. So it's even degree, has a leading coefficient that's positive. So remember, it's like a parabola that kind of opens up like that, okay? And it has x-intercepts as 0, 1, and 3. So let's get that in. So 0, 1, and I'll put 3 about there. Now, because we have the x minus 1 squared, that makes the 1 what's called a double root. It's also a turning point. And so we know the graph looks like something like this right here. Oh, sorry, that's not correct. So it goes like this. 1 is the turning point. And a very, very rough sketch of the graph. And that's all we really need in this case to answer this problem is a rough sketch. So we're interested in knowing when is this greater than or equal to 0. Well, remember a graph shows you all the possible values for this function right here. When is it greater than 0? Well, it's greater than 0 when x is less than or equal to 0. It's also greater than 0 when x is greater than or equal to 3. So there's our two solutions here, greater than or equal to 3 or less than or equal to 0. We also talked about a more algebraic solution without needing to sketch the graph. And in that solution, we made a table. And we said once you have something factored, you can determine whether it's greater than or equal to 0 by considering each factor and whether it's positive or negative, and whether that results in something that's positive or negative at the end. Now, I called these, the columns up here, I called them like regions. So once it's factored, you know that, once it's factored, you know that it can only, these factors can only change signs at one of the x-intercepts. So we have x-intercepts here at 0, 1, and 3. And so 3 x-intercepts will break the graph up into 4 different regions. One before 0, right here. One between 0 and 1, right here. One between 1 and 3. And then one after 3. So all we do is we think of a number. It doesn't actually matter in this case. Any number less than 0, we know whether these will be positive or negative. It doesn't matter what number you pick less than 0. You can pick -1, you can pick -10, it doesn't matter. So if x is less than 0, in my head I'm thinking about a number like -1, then x is negative. Okay, x minus 1 squared is positive. Okay, -1 minus 1, -2 squared is positive. And -1 minus 3 is negative. And now what I need to do is I just think, okay, a negative times a positive times a negative is always a positive. So the final answer will be positive, okay? Because the equation is made up of these 3 factors. So their signs determine the sign of the answer. You could also notice that x minus 1 squared will always be positive. No matter what number you put in for x, once you square it, you get a positive. So I could speed things up a little and realize that all of these are going to be positive numbers. Okay, moving on, a number between 0 and 1 might be like a half. Okay, well, if x is a half, then it's positive. If x is a half minus 3 is a negative number. And now I have a positive times a negative, which is a negative. For the next one, I think of a number between 1 and 3. Seems like 2 is a pretty good answer. Well, if x is 2, then x is obviously positive. Okay, if x is 2, then this is negative. And a positive times a negative is a negative. Moving on to the last example, think of any number bigger than 3, like 4. Okay, well, if x is 4, then x is positive. This is positive, and all 3 factors are positive, and we get a positive answer. Sure enough, that gives us the exact same solutions that we had before, that either x is greater than 3 or less than 0. And we included the greater than or equal to sign because we had the greater than or equal to sign right here as well. Just a way of explaining, a different way of thinking about it. Like why our 2 answers are x less than 0 and x greater than or equal to 3. Well, why does x less than 0 work? Because when x is less than 0, x is negative, this is positive, and this is negative, and that gives you a positive answer. Why is x greater than or equal to 3 and a possible answer here? Well, because when x is greater than or equal to 3, all 3 of these factors are positive. A positive times a positive times a positive gives you a positive answer. So this algebraic method is very important going forward because it's really the best way to solve rational inequalities, in some ways the only way. It's very, graphing rational functions can be done, but it's difficult as you've seen. And so when we solve a rational inequality, we tend to do something like this table here. So let's move on to that next. So our first rational inequality is a fairly simple one. X minus 2 is less than 8 over x. So let's take a stab at doing this. Something we might try to do, and we're actually, this is incorrect, by the way. So just, I'm showing you something and we're going to look at it and try to figure out why it doesn't work. Okay, so you might try the following. Multiply both sides of the equation by x, so it's no longer a rational inequality. Well, that seems to make sense. And then we get x squared minus 2x is less than 8, or x squared minus 2x minus 8 is less than 0, which actually factors nicely to x minus 4 and x plus 2. And then we could try to find our solutions. We could do it, it's now a polynomial inequality. In fact, it's just a parabola. It's pretty easy. It's going to have an x-intercept at 4, another one at -2. It opens up. And so we see it right here. And we can say, okay, we want to know when it's less than 0. So our answer is -2 is less than x is less than 4. And we feel like we're pretty good with that solution. But it's not correct. So why isn't it correct? Well, let's just take a look at some of the answers we come up with. Think of numbers between -2 and 4, like 3. Okay, 3 minus 2 is 1, and 8 over 3 is 2 1/3. So yeah, 1 is less than 8 over 3. So x equals 3 is an answer, and it works. But how about x equals 3 works. How about x equals 1? Okay, 1 minus 2 is negative 1, and 8 divided by 1 is 1. So that one works as well. Negative 1 is less than 8. How about x equals 0? Ooh, we got a problem now. X equals 0 is in this interval, so it's supposed to be a solution. 0 minus 2 is negative 2, but 8 divided by 0 is undefined. So we got a problem right there. The problem isn't just with 0, though. How about x equals negative 1? Negative 1 is between negative 2 and 4. And yet if you plug negative 1 in here, you get negative 3 on the left side, and on the right side you get negative 8. Well, negative 3 is not less than negative 8. So this solution can't be correct. And the problem is it has some numbers that it's correct for and some that it isn't. So it's a real problem. Another way that we could see that it's not a correct solution is we could look at this inequality. We could look at its graph. So I'm going to throw both equations, the left side of the inequality and the right side, in Desmos and see what we get. So there they are in Desmos. I've got y equals x minus 2, which is the blue line. I've got y equals 8 over x, which is the green line. And then down below here, I've put the inequality in here just so we can see it. So we're interested in knowing when is x minus 2 less than 8 over x, or when is the blue line less than the green line, which means when is the blue line lower than the green line? Well, it is definitely lower. Let's figure out where that point is, 4, 2. It is definitely lower than the green line between 4 and 0. Okay, now you can't actually evaluate 0 here, but it definitely is. But then after 0 in the negative line, it's actually higher than the green line. So you can see that doesn't work. Okay, that can't be the solution. Okay, because here the blue line is actually greater than the green line, not less. So it's not the solution we want. We actually want these solutions in here. I know the graph can be a little bit confusing, but I still wanted to take some time and show that to you. The problem that we have here is actually very similar to the very first example we did in this lesson. If I just back up. Remember that when we divided by a negative sign, we needed to flip the inequality. And the same kind of issue right now. Because we multiplied both sides of the equation by x, and x might be a negative number. So when we multiply or divide an inequality by a negative number, we have to flip the inequality. So if x is negative, we need to flip the inequality, but x could be negative or positive. So which is it? It's just not a good approach. So you don't want to do this. So what is the correct approach? Well, similar to how I solved rational equations in the last lesson, I'm going to set this to 0. Okay, starting with x minus 2 over 8x. I get that right there. Okay, this can be simplified using a common denominator. If I multiply x minus 2 by x, I can write it as x squared minus 2x minus 8 over x, all less than 0. Now, don't multiply both sides of the equation by x, though, in this case. If you were solving, if this were an equal sign, great. Multiply both sides by x. X can't be 0. Okay, we should write that as well. And go. But we're not doing that. We're going to leave that there. Now, we can factor this numerator, so we'll do that as well. And then we're going to take an algebraic approach, just like we did with the last polynomial equation, where we break this graph up into its factors and its regions. Now, this graph actually has it's kind of like it has 3 factors because you're multiplying and then dividing. So if we want to know when this is less than 0, we want to think about, one way it could be less than 0 is if this is a negative and this is a positive and this is a negative, because a negative times a positive divided by a negative would always be negative. Another way it might be negative is if all 3 of them are negative. Negative times a negative divided by a negative would be a negative as well, so it would be less than 0. So we know our factors, so we know the left side of the table. We know that these 3 factors determine the sign of the final answer down here. So that's what I put in here, okay? Anything that appears here, any factor. My regions are a little bit different. So if you want to think of graphs of rational functions, And think about when graphs of rational functions could change sign, okay, from positive to negative. When they cross the x-axis, that could happen. So the x-intercepts at 4 and 2 give us, or negative 2, pardon me, give us 2 of our regions. So I know that this will have an x-intercept at 4 and another one at negative 2. But another thing that can happen is the graph can switch signs after a vertical asymptote. So at x equals 0 is a vertical asymptote, so there's another place where the graph can switch from positive to negative or vice versa. So in this case, I have 3 important values that split the graph up into 4 regions. Before negative 2, between 0 and negative 2, between 0 and 4, and after 4. And sure enough, there's my 4 regions right there. And now the problem is just the exact same as the polynomial inequality. So think of a number less than negative 2, like negative 3. Negative 3 minus 4 is negative. Negative 3 plus 2 is negative. Okay, if x is negative. So we have 3 negatives, which gives you a negative times a negative divided by a negative will be a negative value. Think of a number between negative 2 and 0. Okay, so like negative 1. Okay, well that will be negative. This will now be positive, and this will be negative. A negative times a positive divided by a negative will be a positive. You don't even need to think about dividing. It's the same rule as multiplying. Think of a number between 0 and 4 like 1. We would have a negative value, a positive, and a positive, which gives us a negative. And then finally, think of a number greater than 4 like 5. We will have a positive, and a positive, which gives us a positive answer. Now, in this question, we were looking for when is it less than 0? Okay, well, that happens right here and right here. And so our two solutions are either x is less than negative 2 or x is between 0 and 4. Two solutions. Now keep in mind when you do these answers, I don't have the less than or equal to sign, okay? But you can't have 0. X can't be 0. When you write your answers, I just make sure you keep that in mind. X can't actually be equal to 0. So I could never say greater than or equal to 0 because it can't be equal to 0. So just be careful with that. Okay, one last example to look at. X plus 3 divided by x plus 1 greater than or equal to x minus 2 over x minus 3. Now, hopefully you realize from the last example, you cannot cross multiply here. And the reason that you can't cross multiply is cross multiplying involves multiplying both sides of the equation by an amount, and that amount is going to be an x in it, and x could be negative. So we can't do that. So instead, we're going to, it's very easy to look at equalities and compare them to 0, or it's easier, so we bring that over and we do that. We're then going to make a common denominator to simplify this expression. That common denominator is x plus 1 times x minus 3. Okay, so I multiply this guy by x minus 3, so I have to do the same thing on the top. I multiply this guy by x plus 1, so I have to do the same thing on the top. And then I can combine them, of course, since they have this common denominator. Next step will be to expand. So I'm going to use FOIL and expand x plus 3 times x minus 3. I'm also going to expand over here using FOIL, okay? But be careful, because when you do that, you're subtracting that result. So you want to keep those brackets there when you do that. And that's what you get. Okay, you distribute the negative sign now. And you get x squared minus 9. Take away x squared, negative times a negative, positive x, positive 2. Finally, it simplifies to x minus 7 over x plus 1, x plus 3 greater than or equal to 0. Our next step is now to put this in a table and determine what the possibilities are for when we could have a value greater than or equal to 0. Now let's think about the factors are pretty easy. There's 3 factors there. But keep in mind, let's think about what the regions would look like. So we can think about what the graph of this would look like. It would have an x-intercept at 7. Okay, it would also have vertical asymptotes at 3 and negative 1. So there's 3 important places on the graph, negative 1, 3, and 7, which breaks, again, the graph up into 4 regions. One before negative 1, one between -1 and 3, one between 3 and 7, and one greater than 7. Let's look at our table now. And there it is. And once you've got the table set up correctly, it's just a matter of filling it in. So think of a number less than -1, like -2. Well, that's going to be negative, x minus 7. That's going to be negative. Okay, -2 plus 1 is still negative. And we have a negative divided by a negative times a negative, which is negative. Think of a number between -1 and 3. Oh, we better be careful here. Let's keep in mind that we can't actually have, I should have mentioned this earlier, x cannot be -1 or 3. So those values actually can't exist. Okay, so a number between -1 and 3, 0 is a nice one to use there. 0 minus 7 is negative. 0 minus 3 is negative. 0 plus 1 is positive. A negative times a positive gives you a positive answer. In this case, a negative divided by a negative times a positive is a negative divided by a negative, which is positive. A number between 3 and 7, let's use like 5. It's going to be negative, positive, positive, and I get a negative result again. A number greater than 7, like 8, I'm going to get a positive, 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 and so final result that's positive as well. Now we're interested in knowing when this is greater than or equal to 0. So our two solutions are right here, but keep in mind x cannot be equal to 3 or -1. So one answer is -1. Sorry, x is between -1 and 3. The other answer is that x is greater than 7, and x can be equal to 7. If x is equal to 7, it's equal to 0, and we want to include 0 as our answer. So for that, we actually say x is greater than or equal to 7. And that's it. The only other tricks that I will mention is be careful if we had something like this. If you had, I've seen this in class before, suppose you factored this and you had a negative out front. That's like a -1, in which case -1 now needs to be one of your factors as well, because it doesn't change the sign of x minus 7. In which case you can just put -1 as one of your factors, and it's always negative, regardless of what x is. So just be careful with that. I thought I'd better mention that in case you come across that. Okay, that's it for this lesson. Thank you.